Okay, it seems that we are live. I just want some confirmation that everyone is hearing me correctly. Please type in the chat. Welcome, everyone. Good morning. Um, Perfect. Thank you for confirmation. Okay, so let's begin. So, welcome, everyone. This is the first session of the new series of webinars for the Power Conversion series, which is something that we do every second Thursday of each month. So, this is the first installment. Today's session will be hosted and presented by me, Juan Rosales. I'm an application engineer for electronics here at Siemens. And on the chat, and a coworker of mine, also application engineer for electronics or for power conversion, Nikos Mitrakopoulos. He's going to be monitoring the chat. He's going to be answering questions as they come. Maybe he's going to be, interacting with you guys through the chat. So, yeah, good evening to you too. Thanks everyone for coming. Thanks everyone for commenting. Let's begin. So optimized component selection for multi-stage power conversions systems. This is the title of the webinar. So let's see what is it about. So what's the objective? So for the power conversion team here at Altair, or at Siemens, I apologize. We've been working a lot on automation and optimization for power electronics. So the idea is another proposition of these optimization workflows. The idea is to develop a simulation-driven optimization workflow that allows us to select between these transistor technologies across multiple stages of a power conversion topology or of a multi-stage power supply, right? The main focus of this workflow is to optimize the efficiency, cost, and surface area, which are very important pain points in today's design, specifically for data center GPU or data center in general power supplies. So and then eventually we will generate a bunch of data, and with that data we will be able to make decisions essentially. So what's the origin of all of this? Maybe a bit more specific. So we saw this. We saw a schematic similar to this one at an application note from a semiconductor company, and this was for a power supply for a data center. And the interesting, the thing that we saw and that makes sense is that they use different transistor technologies for each stage, right? And the question is, could we automate, or could we optimize, or could we automate the optimization for the selection of these devices in these stages? We also, on this topology, you would expect, and that's what happened, that there are interleaved and parallel configurations. So the idea is, can we get to that conclusion with optimization and Altair tools, right? So that leads me to the tools. So today we're going to be working with two tools. We're going to be working with PSIM, which hopefully you're familiar with. PSIM is a power electronics simulation tool. It helps us do control design, and it allows us to also do electrical and thermal simulations, which is something that we're going to be using a lot today, since one of our optimization goals is efficiency. And then we're going to use HyperStudy, which is our design exploration tool, design optimization tool, and it's also what automates all this workflow, right? So looking at the case study, if you weren't, very quick at looking at the previous topology, here it is in full. So we have on the front end an interleaved totem pole PFC, and on the back end we have full bridge resonant LLC with active rectification. So essentially, we have a bunch of positions for switches and a lot of opportunity for this optimization to happen. So, okay, let's look at the challenges that we want to focus right now. So we want to, as I mentioned briefly on the motivations, we have the losses, the cost, and the thermal layout. So switching and conduction losses will vary depending on the transistor we choose, which is obvious. The cost is also something that impacts if we are comparing parallelization with lower rated components or higher rated components and just using one or two. And that's also something that can be a very heavy thought experiment if we do it maybe by hand. And also thermal and layout, right? So surface areas related to cooling and power density. So we want to take that into account as an output of this optimization. So something I want to mention that is pretty important is what this session is and what is it and what it is it not. So this is not the whole picture, right? This is just a focus on these three characteristics of design. This is not intended to be a lecture on how to choose these devices, on how to design these topologies, or on yeah, it is not a lesson for those things. It is um, an idea that we had for an optimization workflow, and yeah, just to see if we can do this, to see if we can reach some sensible or some accurate conclusions with the tools, right? So yeah, so you will see that there's not a lot of theory in that sense here. It's all about simulation tools and simulation driven design. So for that, everything is built around these thermal models in PSIM. If you're a PSIM user, which is very likely you already know these. So thermal models are those which are based on lookup tables. These models, these lookup tables we obtain from datasheets or from vendors. And they allow us to get pretty accurate losses without sacrificing the simulation speed. Essentially, these are ideal models, so a perfect transition between on and off states. But behind them, there's a calculator that calculates losses accurately depending on the operating point and the temperature of that device. So yeah, and those are the models that we're going to be working with. So looking at the overview of this workflow, the first step is device pre-selection. So I'm gonna, beforehand, I selected a set of GaN transistors, silicon carbide transistors, and silicon transistors that were suitable for these designs. My criteria is not covered in here, but we can talk about that later or in another moment. But yeah, I pre-selected a set of these so that the optimization is pretty much self-contained into those devices. Then electrical and thermal simulation will take place, which will lead us to the multi-objective optimization. And then we'll just check the results and compare trade-offs and look at the outputs, right? So let's continue. Okay, so starting from the device pre-selection, these topologies and each stage of these topologies have constraints and have design requirements. So I chose these 12 devices that we can use and that the optimization algorithm will choose for different, in different configurations and in different places where it makes sense, right? So this is exactly what I mentioned earlier. So just reduce the candidate pool and focus on what it is possible and what's not exact, so that the optimization algorithm is doing most of the work, right? So all of these are possible, but not exact. This is why I chose a bunch of them. And as you can see, a interesting detail here. While again, these are not the only ratings I considered, but something that I want to point out here is looking at the currents. These currents, the current ratings are very different, and they go kind of like from top to bottom in that sense, from high current rating to low, or from relatively high to relatively low. And the idea is that the optimization algorithm will also choose which of these devices to parallelize to meet the design requirement, which is something that I thought it was pretty fun for this experiment or for this workflow. So yeah, now talking about how we are simulating all of this. I'm talking about the electrical part, or so these stages, the PFC and the DC-DC stage, are gonna be simulated independently. There is no cross-stage electrical coupling. These are not gonna share any information between them, which allows us to simulate very nicely in parallel um, these two topologies, which allows us to be computationally more efficient. So the optimization can be quicker in that sense. We should be able to do this. If you want to put this together, you should be able to do this, no problem. I just wanted this to be faster, while focusing on the goals that I had in mind. So yeah, with this, I think it's time for us to go to the tools. So first, let's go to PSIM. And this is how, and here I have opened both simulations that we're going to be working with. And so yeah, here's the interleaf totem pole PFC. Fairly straightforward control. And there's a couple of details in here. So if you know PSIM, you can see, you know that if we double click any model, we can see its attributes. And you'll see some of these attributes are parameterized. This means that we place a variable, and to that variable we assign a value. And parameters correspond to the device model, to the number of parallel devices, and the turn on or the gating characteristics or the gating resistance. So this happens for all of the switches in all of these examples. And how is it related to the optimization? This is how we control which model and how many devices we are using per switch position in the optimization. And we can see how we deal with that also here. So these are the explicit variables we're going to be changing with HyperStudy. And in here, there's the logic behind these indexes, because if you see the device index is a number, not kind of like a string with a model, but this number will imply a model, a device model, and an on-off resistance. And the same thing goes for this low lagging here. So we have this conditional logic so that we can, so according to one index, we can select a model. Another detail here is looking at the thermal models, the switch thermal models. We have this case node. This case node is connected to kind of like a dummy heatsink. So all of these transistors for now would be interfacing to the same point with a heatsink. Now, again, this part is not supposed to represent real life that accurately. Again, this is for the purposes of demonstrating this idea. So yeah, what we get is we have a very simple thermal circuit, and what we do is with measuring power as a current through this thermal network, and we calculate the sum, and then we get the total power that comes from the switches. So conduction and switching losses all are summed up, and that is going to be one of the outputs from this topology, right? Right now, we're only caring about the output losses from the switches specifically for this optimization. So yeah, so the same thing happens with the resonant LLC. The only difference or detail is that some components don't have a thermal model, which is something that if you're a user, you have faced at some point. So alternatively to the MOSFET EON model, we have another MOSFET thermal model. And this is why we have two subcircuits here. These two subcircuits are toggled depending on which type of model we are using. When we have EON models, we use this one. When we don't, we use the other one. Okay. So another interesting detail about here, which is me trying to be me trying to let HyperStudy do an easier task when analyzing information, is that if I simulate this, let me hide, let me wait for a second, and we look at the outputs, we can see that the resolution of these plots is not the best. And this is not because I have a very large time step. Actually, a time step is pretty accurate or pretty adequate for these simulation. But what I did, and let me look at the simulation settings. Where are they? Here they are. And if we look at the simulation settings, we do have an actual useful time step for this topology, but the print step is what I've changed. My goal with this is that we have less data points so that it is easier for HyperStudy to analyze these time series, which is something that impacts in the speed of optimization. Okay, so I believe I covered everything regarding PSIM. Yes. Okay. So let's jump into HyperStudy and let's see what's happening in there. Okay. So this HyperStudy, if you don't know it, I'll try to guide you through the steps on a high level, because if I do this from scratch, it would take like double or triple while I'm explaining it. So this is already done and solved, and I am gonna look over the steps on how I did it. So first, study needs models to work. A model can be a PSIM simulation. So what we do is click here, add model, select the PSIM simulation, and then we import the variables. The variables are what we parameterized in this parameter file specifically. And there's another parameter file like this one in the resident LLC. So this is what HyperStudy is going to read. And if we go to the next section, which is the input variables, these are if you look at the labels here, these are the variables that we read from PSIM. So here in this part is where we select the bounds for the variables. If we go back to this part here, to this part here, we can see that we have different indexes for these devices, and I've located, or I've organized these indexes so that we have the 650 volt rated devices from 1 to 7, and the 100 volt rated devices from 8 to 12. So the indexes are selected accordingly. So we have here a lower bound of 1, an upper bound of 12, or 4. A lower bound of 12 for the index. And if we see the constraints, these indexes are related. Let me rephrase. So each index, we have 2 indexes per topology. We have the ones for the LLC, we have the ones for the PFC. And these need to be constrained because of the voltage ratings. So this is what this part means. So the index for the 650 volt switch positions, if we can call it that way, need to be lower than 7. So that's what these constraints mean. And the other indexes, or the other variables that we are changing, is the number of parallel positions or parallel switches, which in this case I've set from 1 through 4. Okay, so that's what this means. And then the next step for HyperStudy is to test these models. What it does, it is copies everything, every asset, every simulation file. It puts it in another directory and it runs the simulation. And from that, we can get what we call output responses. So let's first talk about data sources. So an output response is the output of PSIM simulation, which is everything that we can see here in SimView, which is just a set of tables, right? A set of curves. And with this file assistant, we can read the output of a PSIM simulation. So in the end, what we can get from there in each curve is what we call a data source. With data sources, we can make operations and create output responses. And with the example, that will be clearer. So as the data sources, I have two main sources. I have the output of the simulation and a CSV file with a component list, which is this CSV file. So this CSV file has the same table that I show you in the PowerPoint presentation. And what I do with these is pretty interesting. So first, from the CSV file, I'm getting the cost and the area and the surface area of the component, and also their current rating. And then from the output the output of the simulations, I just get the total loss for each topology. Again, just from the switches. So remember, the specific focus of this optimization was cost, area, and power or loss or efficiency. And this is what we have here, right? So nothing else. So what are output responses? Output responses would be the total cost of both topologies. So how much did the cost of the switch, how much is this total cost of the switches in both topologies? The same thing with area, the same thing with losses. And I'm also placed a constraint on the current. So for parallelization, it is evident that if I'm going to put if I put a device or two devices, the maximum current for those two devices needs to be the rated current for the design, right? I cannot put, for instance, just one 30 amp switch when I'm expecting 100 amps, right? So this is what this constraint means, and maybe having it more explicitly here in this slide might help. So how we are calculating total cost, which is what we have here, maybe not so explicit and easy on the eye. What we're doing is just multiplying the number of devices and the type of device for the cost of the device. In the case for the cost, we have the complete sum of the devices in each position. So on the primary side of the LSC, on the secondary side of the LSC, on the fast leg of the PFC, and on the slow leg of the PFC. And this also accounts for parallelization. The same thing we do with surface area, and the same thing we do for the constraint, which is current per switch position, right? So this is what I meant. So the number of devices per switch position times the current or the rated current that we get from the table has to be more or equal than the maximum design current, right? The rated that I calculated beforehand. So that's what is here output responses. And regarding goals, which is what we have here, we just tell the tool to minimize cost, area, and losses while keeping the constraints that I mentioned before. Okay, so with this, we can just set up an optimization. So this is just a setup, and in a HyperStudy, from a setup, we can do whatever, right? In this case, an optimization. So we already defined the goals, we already defined the models, we already defined everything. And this is the base here that's called definition. Here on the specifications part, we select the optimization algorithm. In this case is GRSM. And if you want more information about this, we can send it to you. But we also have a lot of tutorials in YouTube around this workflow, if you want to check those out. And here is the evaluations. So HyperStudy in total did 200 simulations, which took around an hour to simulate. So with all of the considerations I took for optimization speed, we had around an hour to wait for results. So this is how the evaluation data looks like. We have this table that might be a bit hard to read, but in trying to decompose it, so here are the indexes that we are changing. So going one by one, for instance, this is a device index. So each one of these numbers represents a device. The same thing with this one. This is the number of parallel devices in one position. This is the other one. The same thing happens for the PFC. And here is the total cost, total area, total losses, and the rated currents calculated in these columns. And the goal columns are exactly the same thing than these two, right? So the goals and constraints were cost, were losses, were surface area. So in here, we're going to see some qualifiers or some qualifying words, whether a simulation combination is feasible or if it's not feasible, if a constraint was violated, for instance, for the current of parallel devices. And if we keep scrolling down, we'll see some in green, which the algorithm determined were the best possible outcomes. And so here's where we can start looking at trade-offs, for instance. So here we have the total cost, and we can sort down these. We can sort down the results for cost. So the lowest cost is this setup. So we have device number 7, we have device number 9. We have a single device in these positions. And then for the PFC, we have these two devices. We have one device just for the fast leg and two devices for the slow leg, which makes sense that it is the most efficient in cost, right? But let's pay attention at the other constraints, right? So total area, it's 100K millimeters, and total loss is 134 watts. So let's kind of put a pin on that, and while we start looking at the other most efficient choices. So if we go for total area, the same choice is going to be also the most efficient one. But if we go to losses, we can see that the most efficient one regarding losses occupies triple the space, and it is around 3 times more expensive. So if we were to choose this option, this would not be, super efficient. And if we maybe choose the one that's more, the one that's cheaper or the one that's smaller, we won't be choosing the best option. And this is where we have to start thinking about our own criteria, right? So this is all data. This is not exactly a decision. We still have to analyze everything that we have here and take a decision, right? So I made a quick, comparison table between this. So if it wasn't pretty much clear, so we have these two topologies here, and then here we have the selected combinations and the devices. So the best option for total losses are 4 parallel devices in fast and slow leg of the PFC, and 2 parallel GaN devices for the inverter, and for the synchronous rectification, just 1 parallel silicon device. So we have the same thing for the option for the best option for total cost, the best option for total surface area, and the best option overall is a personal choice. So from the green options that we had in this table, I chose one because it seemed to me the best one. Again, this may differ from person to person. These are all possible choices. We just need to, start using our criteria to select the best one. But in here is where we look at the trade-offs, right? So the trade-offs are here in orange, and we can see that it uses 80% more space than the most surface area efficient option. And if we look at, if we go back to here, we can see that total area was 3, like if we look at the most optimal in terms of switching losses or transistor losses, it was 3 times, the total area that was 3 times of the smallest one. So 80% larger than the smallest one is a very good compromise. So this is what I meant in the beginning. The idea is this is not by any means a complete solution to choosing devices, it is an idea, it is a proposition for a workflow that can be enhanced, that can be expanded with other conditions, with other constraints, with more devices, even with more goals, with more inputs. But this is this is just very self-contained, and this were the results of this. And if we actually compare this to what we had in the original, so having silicon carbide for the PFC, having GaN for the primary, and having silicon for the secondary, this is very similar to this configuration, or the devices that were chosen were pretty similar to those ones. So we can see that this workflow, or the outputs, even with these constraints, have outputs that make sense, right? Okay, so with that, we end this webinar. So thank you everyone for coming. Expect more content coming from the team. Keep an eye out on the next webinars, and thank you for coming.